Thank you. First, I wanted to acknowledge my co-authors, Mike Way and David Amundsen, who did a lot of the work for this talk. And I'm just the one up here delivering the talk. And the background of this slide is what a climate modeler would like to believe that Proxima Centauri b would actually look like if you were there. But according to a number of people, including people in this room, Proxima Centauri b probably doesn't have an atmosphere. If it has an atmosphere, it probably doesn't have water. And I think we're going to hear another talk by Rodrigo in a little while talking about the same type of thing. And so, but if you read these papers, at least a couple of them, it may have water. There are ways. It could have formed farther out and migrated in. It could have been formed with tons of water and not lost all of it. Could have formed with a hydrogen envelope, and that burned off and left something reasonable behind. So there are ways it could happen, and so it's interesting, actually, as an experience to get up and give a talk about an atmosphere that may not actually exist. But for the purposes of the next 10 minutes, let's be optimistic and imagine that it does exist and imagine what possible climates of such a planet might look like. And so climate models are optimistic in general. We have to be. So I model 21st century Earth climate change, and if you're not an optimist about things, it'll just drive you crazy. So anyway, other people have tried to model the climate of Proxima b, assuming it has different kinds of atmospheres, and you can change the kind of atmosphere and get more warming and less more greenhouse warming, less greenhouse warming, and so on. People usually start with Earth-like type atmospheres with about a bar of nitrogen with some modest amount of something like CO2 and so on and so forth. And here are two examples from the literature, from Turbet et al. Using the LMD model, and from Boodle et al. Using the British Met Office model. Both of them making the same assumption with an aquaplanet, that is an ocean-covered surface, no exposed land, and a static ocean, a thermodynamic or slab ocean. And so the ocean sits there, it absorbs sunlight. If it absorbs enough starlight, it is liquid. If it doesn't, it turns into ice, it evaporates water, does things like that, but it doesn't move around. And so basically at the substellar point here, you get liquid water, and outside the 0 degree C line, you get ice, all right? And you can see similar results in both models. And so for this type of planet, what happens at the substellar point stays at the substellar point. And Ray-Pierre Humbert called that configuration eyeball Earth, all right? And that's sort of the typical way that people who use 3D models try to simulate exoplanets, because it's the quickest way of doing those calculations. But oceans are a lot more interesting than that. They do other things that actually matter to the climate. So oceans have thermal inertia, and depending on how deep you assume the ocean is, it can have a lot of thermal inertia, which really slows down the response of the climate to a change in installation, all right? Oceans transport heat. In GCMs without a dynamic ocean, the atmosphere transports heat, but the ocean does not. Oceans transport heat and make it a lot easier to keep things warmer over a larger region of the atmosphere, but they take heat away from the substellar region, as we'll see in a minute, and keep things cooler there. And that was demonstrated in a paper by Hu and Yang 2014, who used a dynamic ocean to simulate a generic planet orbiting an M-star. And then another point that hasn't been emphasized very much, except in this one paper by Cullum et al., is that oceans have salt in them, and salinity depresses the freezing point. That's a good thing if you're trying to make a habitable planet. People do a lot of experimentation with the composition of the atmosphere. They don't do much experimentation with the composition of the ocean. So let's look at a couple of those things. So we're doing our simulations with a different 3D general circulation model called Rocky 3D that's developed at NASA Goddard Institute for Space Studies as an outgrowth of our terrestrial climate model. And that model is described in a paper. Oops, sorry, I went the wrong way. How do I go back? Let's see. There we go. It's described in a paper by Mike Way et al. That's been posted on the archive, and it's under review in AbJ supplement series. It's a 4x5 degree model with 40 layers in the atmosphere. We're using a 900 meter deep ocean with 9 layers, assuming an aquaplanet like the previous studies. We're doing runs with synchronous rotation, but we're also doing runs with 3-2 spin orbit resonance, one with 0 eccentricity and one with 0.3 eccentricity, which is close to the upper limit that people think is reasonable. We're using sort of typical faux Earth type atmosphere for today's talk, but we're trying other compositions. And we're using an ocean with different salinities, something typical of the Earth, something that's freshwater, and something that's more like the Dead Sea. And so here are examples of what you get with such a model. On the left, just as a sanity check, we ran our model first with the thermodynamic ocean that the previous modeling papers used, just to show you that we can get the same result for that type of simulation in eyeball Earth. But now here is the result for the ocean, the dynamic ocean, and it looks very much actually like what Hu and Yang saw in their 2014 paper. What happens is that in response to the heating at the substellar point over here, you get these atmospheric waves, Rossby waves, on either side of the equator, upstream of the substellar point, and then you get a Kelvin wave downstream. It creates this unusual pattern of above freezing temperatures. And I should say, by the way, that I'm using a color bar convention in which the transition from blue to yellow is the transition from below to above freezing, not below to above 0 degrees C, because it's different with salt. So anything that's yellow is liquid water, and this was called by Hu and Yang lobster Earth instead of eyeball Earth. And you go from a planet that has only 20% open ocean without the dynamic ocean to something that has a little bit more than twice the open ocean. Even though the maximum temperature at the substellar point is a lot cooler than it is with the thermodynamic ocean, still this barely above freezing seemingly water is covering a fairly large fraction of the planet. Okay. Something else people worry about for habitability is the transition to a moist greenhouse, especially around planets around M stars, where there's lots of shortwave absorption by water vapor that can wind up putting lots of water vapor into the stratosphere and get you to a non-habitable climate sooner than you'd like, and that's a concern for M stars. This is a figure from a paper that we have in review by Yuka Fuji in AppJ, showing how the stratospheric water vapor changes with total incident flux for 4 different kinds of stars here. This is the same thing plotted versus surface temperature at the substellar point, and this is the same thing plotted versus the near-eye R flux, which is actually the fundamental parameter for stratospheric water vapor. Just to show you, Proximab B just gets too little installation. It's nowhere near this place up here where you start to worry about moist greenhouses. So whatever else may be bad about Proximab B, moist greenhouse is not one of them, given how little installation it receives. Okay, on to more exotic types of oceans. On the left, we're showing the result with the experiment in which we've used a freshwater ocean, 0 salinity, and on the right, we've used this Dead Sea salinity of 260 practical salinity units. That's grams per kilogram. We'll talk about the freshwater case first. You can see compared to the nominal lobster Earth pattern, the pattern is still there, but it's a lot smaller. This is kind of a baby lobster. The reason is that in the ocean you have 2 different kinds of heat transport. You have a wind-driven heat transport that's usually in the upper layers, and then you have a density-driven or thermohaline circulation in which the density differences that drive it are due to temperature differences and salinity differences. You take away the salt and you only have the temperature component, so you weaken the thermohaline circulation, you can't transport as much. And then there's the peculiar feature of fresh water that its density peaks at 4 degrees C, which is not the case for salty water. And so as you move away from the substellar point and move towards 0, you actually get to this 4 degrees C contour, and all the water starts to sink around the edges there, and it's not available actually to transport the near surface water around to the night side. So you get a very confined region of open oceans, only 32%. But you go to very high salinity, and pun intended, take this simulation with a grain of salt. This ocean model was not intended to go up to things like 260 PSU. But the one thing that you probably can count on is that the freezing point is very, very depressed at 260 PSU. It's down near it's about at the eutectic point. It's about close to minus 21 degrees or something like that. And so you wind up having a planet that is not above 0 degrees C anywhere on the planet, yet 97% of the planet is liquid water, okay? And so you don't have to build up bars of CO2 to make a planet that is technically habitable in its ability to sustain surface liquid water. You can make something that looks completely cold but still could be habitable with the price you pay, that it's really, really salty, okay? Is a really, really salty ocean conceivable? Well, maybe. I don't really actually know that much about that, but people who study Europa, there's a paper from Hand and Chiba where they used Galileo magnetometer data to try to figure out how saline Europa's subsurface ocean may be. And in the end, they kind of came to the conclusion, and by the way, Europa they think is not a sodium chloride dominated ocean. They think it's a magnesium sulfate, Epsom salts dominated ocean. But they came to the conclusion that the Galileo magnetometer results are actually most consistent with a salinity of that ocean that's very close to saturation for magnesium sulfate. And so the idea of a really, really salty ocean, we may actually even have an example right in our own solar system, who knows. Could anything live in an ocean that's salty and that cold? Well, it's amazing. This is a paper by Mike Kittrick et al., 2012, and they found this halophile, Planococcus halocriophyllus OR1 in Arctic permafrost, and they brought it back to the lab and got it to grow and divide at minus 15 degrees C at 180 practical salinity units. So, not bad. Life will find a way. It's amazing, right? So the other thing that we did is to try to simulate Proxima Centauri b now not in synchronous rotation but in 3-2 spin orbit resonance. You get a very different situation depending on whether you assume there's any eccentricity or not. Without any eccentricity, this is the pattern of incident stellar radiation. Without any eccentricity, then you get a climatologically even. There's a diurnal cycle, of course, because it's not in synchronous rotation, but you get a climatologically even pattern of installation at all longitudes. But if you add eccentricity, this is the 0.3 case, then you don't, because then basically every time you come around again, a different side of the planet is facing the star. And so you get two preferred longitudes of high installation with weaker installation in between. So if you apply this type of installation pattern to a thermodynamic ocean like the ones I showed you earlier, then you don't get an eyeball Earth, you get a two-eyeball Earth is basically what you get with ice in between. This is the sea ice cover that we get from the model with the dynamic ocean. With this version of the installation, you melt the planet on the day side in the equatorial region, but it freezes up again on the night side, so you get kind of climatologically partial sea ice cover in a small band near the equator and ice every place else. No place that's completely ice-free. But with this pattern where you're actually getting fairly intense installation in two places on the globe, then you get open ocean, and because the ocean transports heat, because the ocean has a lot of thermal inertia so that it doesn't automatically freeze over once the planet moves over onto the night side, you actually get a permanent, what would people would call a water belt of liquid water all around the planet. So that's a fairly habitable looking planet, and that's with normal Earth type salinity. Okay? So to conclude, dynamic ocean implies that you might have a much colder but a broader habitable region than a static ocean would imply if you have a synchronously rotating planet with an Earth-like atmosphere. If you have a highly saline ocean, you have this possibility of an almost completely liquid-covered planet that nonetheless stays below 0 degrees C everywhere on the planet. And we have examples on Earth of critters that actually grow in conditions like that, amazingly. If you have a planet in 3-2 spin orbit resonance, then with eccentricity, you can produce a nice habitable belt of water around the equator. And of course, all of this is on the condition that Proxima b has an atmosphere and that it has water, which it probably doesn't, but maybe. So let's be optimistic. Thank you.
All right, so we're about 3 minutes ahead of schedule, so we have time for maybe a few quick questions.
So this is with an Earth-like atmosphere, but what happens if you increase the CO2 maybe 4 or 5 times or even more than that?
Okay, so So we're doing runs right now with an Archean Earth type atmosphere. We're specifically doing runs with an atmosphere like what Charnay et al. Looked at in their 2013 paper, their case A, which has, I guess, about 0.9 millibars of CO2 and 0.9 millibars of methane as well. And you get a broader region of open ocean water, but not a completely open ocean region for that. If you go up to very high CO2 concentrations, we have not done that experiment yet, but Turbet et al. Did that experiment with a 1 bar CO2 atmosphere, and for a 1 bar CO2 atmosphere, you can make the planet completely liquid, an aquaplanet.
Cool. Thank you.
Another question about parameter sensitivity. What happens if you change the rotation rate? Does the Matsuno-Gill pattern change as well, or?
So the details of it will change. You'll still get the same basic pattern, and I can tell you that for a fact that it changes the shape a little bit of the pattern, but doesn't change the pattern because the first time we ran these experiments, we mistakenly had a mistake in the code that gave us a rotation rate that was twice as slow as the actual rotation rate. So it changes the look of the pattern a little bit, but the Matsuno-Gill pattern is still there.
All right, make your last question quick.
Okay, I'll hold off on some of the comments that I had. Just a couple comments about oceans in our own solar system. Jury's still out about whether Europa's oceans, magnesium sulfate or sodium chloride, in hand provided a lower bound. The other thing is that if you're looking for a saturated ocean, Callisto might be a good place.
Okay, thank you.
All right, let's thank Tony again.